As we saw, the critical buckling load was written in the form of the Euler buckling load, with the effective length being squared in the denominator. And the effective length is some factor multiplied by L. And this was derived for columns with different boundary conditions, where we obtain different differential equations for each separate case. So for the braced columns, being the three on the left, for a column that's free to rotate at each end, we got k equals 1. So therefore the effective length is equal to the length of the column. And for a case that was fixed at one end and was restrained by a vertical roller at the other end, we got k is 0.7. So the effective length is 0.7 L. And for this buckled shape, the inflection point has a distance of around 0.7 L from the roller. So you can visualize the inflection point as providing the restraint, where you get a transition from tension on one side of the column to the other. And for this case, with fixed to fixed ends, we got k is 0.5, and the distance between those inflection points is around 0.5 L. Now for the unbraced cases, with the first case being a fixed to a free end, we got k is 2. So this gives an effective length of 2L. And you can visualize this by reflecting the column, so it looks something like this. And for this case with a pinned to a rigid support that can displace laterally, making the column unbraced, you'd also get k equals 2. So again, you can continue this column as follows, and it'll look something like this, with the effective length of 2L according to this equation. And for this case with a fixed support to a rigid support that can displace laterally, k is equal to 1. So you can visualize this as this case if you continue the deflected shape as follows, and you'll have your distance between the inflection points as L. Please subscribe, like and comment to help me reach more students.